My name is Alejandra Crespo. I study electrical mechanical engineering. My topic is about verifying the true jitter performance of clothes in high-speed digital designs. We have definition is as the data rates in high-speed digital designs increase, the limits for overall system jitter become tighter. Where I present a video about the accelerating the right clock.
Designers should know whether to select a clock generator, a jitter attenuator, or perhaps even a specialized jitter attenuator for synchronous timing. But how is this choice made? Let's start with a simple question. For these low jitter clock outputs, should I use a clock generator or jitter attenuators, also known as a jitter cleaner? The answer actually depends on the application and the design. Clock generators are typically seen in data center applications like leaf and spine switches. They work best to generate low jitter clocks, but not to clean noisy input clocks. A high-performance clock generator like the SI5391 can be used to generate low jitter clocks. Jitter cleaners are seen in applications like rack systems, where a backplane clock needs to be cleaned and synchronized to the outputs. For these applications, a jitter attenuator like the SI5395 can be used to clean the input and generate low jitter clocks. A clock generator may use either a crystal reference or an input clock as a reference. However, since there is no clock cleaning ability in a clock generator, clock generators perform best when supplied with the crystal input rather than a clock. A high-performance clock generator like the SI5391 that uses a crystal typically has 65 femtoseconds of jitter. Silicon Labs jitter attenuators are typically referenced with the crystal to deliver the best phase noise. However, crystals can have issues with temperature stability and physical vibration and can be replaced with an oscillator, TCXO, or OCXO for improved stability. But since this reference determines the phase noise performance, applications needing low jitter output clocks must use a low phase noise TCXO or OCXO, which tend to be more expensive. A high-performance jitter attenuator like the SI5395 cleans dirty clock inputs to have a typical jitter of 70 femtoseconds on the output clocks. Network synchronization applications such as SYNC-E and SONET and SDH require both good stability and low jitter. For these applications, dual reference jitter attenuator is used. Silicon Labs products like the SI5348, SI5383, and SI5384 are considered to be dual reference clocks since they have two references, a crystal connected to the XA-XB pins and the TCXO-OCXO connected to the reference pins. The crystal works with the DSP-LO to deliver good jitter performance, and the TCXO or OCXO determines both the frequency stability of the device as well as the jitter or wander performance below 100 Hz.
DNN solution. Measuring clock jitter typically consists of measuring the phase noise. For clocks with that high slave relate, the clock jitter is mainly determined by the phase noise of the clock signs. A and M is rarely surprised by the high slave rate of the clock. It typically does not contribute to the overall clock jitter for accurate clock jitter measurement. High AM suppression in the phase noise measurement is important. Wearing the phase noise. Jitter measured in high-speed technologies like PCLE typically need to include the system effect to the TXPLL, RXPLL, and CDR transfer functions. The resulting overall system transfer function is applied to the measured phase noise straight as a wearing filter before entering the jitter in the final jitter integration range. Integrant is about the wearing phase noise. The wearing phase noise is typically integrated to the Nike's frequency of the clock, height of clock rate, and in some cases even above, in that case, the phase noise. Also needs to be measured up to higher frequency outputs. Capturing a clock frequency grid with RF versus time trigger is a video.
Let's take a look at how the new triggering capability in Spectrum View can help us isolate a random transient shift in frequency of this 40 MHz clock. We'll start by adding Spectrum View to the display and then configuring it to look at the fundamental of the 40 MHz clock. So we'll set the center frequency to 40 MHz and we'll also set the span to 50 MHz. Next, we'll add the frequency versus time trace to Spectrum View, which is actually the frequency deviation versus time. And we'll set the trigger to trigger on that frequency versus time trace. Next, we can adjust the trigger level to trigger on a particular frequency deviation value and increase the amount of time we're capturing here to observe the transient. If we pause the acquisitions here, you see the transient frequency deviation of this clock signal in the frequency deviation versus time plot, and the frequency change is great enough that we can even see it in the time domain waveform of our clock pulse. You can see we've got 5 or 6 cycles of the clock here where the frequency is about 10 to 15 megahertz higher than the base 40 megahertz clock. The ability to trigger on Spectrum View RF versus time traces, such as the magnitude versus time and frequency deviation versus time, opens up new possibilities to trigger on and capture signals in ways that were never before possible.
During measurement on IPCL4 Gen CAS cloud. Measuring for cloud in the high-speed digital design has become increasingly challenging. PCL Gen 4, for example, introduced the rate of up to 16 gigatransfers per second (GTS), of course, with a corresponding jitter limit of 500 PSRMS for the reference to clock. To minimize an effects about technologies like PCLE, USB, and HDMI of call user spectrum called clean SSC, applying a low frequency FM to the reference cloud sign and assist both additional stress of the clock about your also needs to verify and ask on move. It is other video about Agilent demonstrates SNGIT USB 3.1 signal analyzer.
Hi, my name is Eric Wong at IDF 2013, and I'm here with
Tim Choate from Agilent Technologies.
So, Jim, what does Agilent do?
We make test and measurement equipment for physical layer validation for USB technology.
For USB technology, great. And you're going to show us some sort of demo around USB 3.1.
Correct.
Great, let's take a look.
So here I have a 33 gigahertz oscilloscope, and I'm measuring a 5 and a 10 gig super speed transmitter signal integrity. So channels 1 and 3 are connected to a simple USB 3 flash drive running at 5 gigabits per second. Channels 2 and 4 come off our high performance bit error rate tester generating a 10 gigabit per second signal.
So these are data inputs. USB 3 in through here, 10 gigabit per second USB 3.1 like signal going in here.
Correct. So if you look at the bit error or the bit times, we have 100 picosecond unit interval on the channels 2 and 4 inputs to the scope. And then using our jitter decomposition software, we're analyzing in real time the jitter on this signal coming in from our bit error rate tester. So when you test a USB 3 transceiver, first step you test the transmitter outputs directly using this system software to analyze your RJ and PJ spectrogram. And then you would also hook up your bit error rate tester to calibrate the signal that's going to go into the receiver to try to break it at the required test points for jitter compliance and receiver jitter tolerance testing.
So if I understand correctly, you're ready to go to test a 10 gigabit per second USB 3.1 transceiver.
We are ready to go. We have the baseline equipment requirements nailed with the scope bandwidth requirements and the bit error rate tester. The underlying algorithms will need to be fine-tuned and tested against the test spec requirements that are under development today, as well as validated against real silicon.
So Jim, if I understand correctly, you're ready to start testing a USB 3.1 10 gigabit per second transceiver.
Correct. We have the baseline hardware requirements with oscilloscope bandwidth as well as a bit error rate tester, but the underlying analysis algorithms will have to be fine-tuned with real silicon and adapted to meet the final test specification requirements.
Great. Okay. Jim, thanks for joining us today.
Yeah, you're welcome.
Wave to the camera.
Applications in electrical mechanical. This especially applies to the various components of the clock tree where the jitter limits of reference closed buffers and jitter attenuators are even tighter. Due to the tighter high phase, noise-sensitive phase noise analyzer are other instruments of choice of the test. Is a video about a clock tree expert boost, PCLE clock generator and buffer bump for you.
Silicon Labs is pleased to introduce Clock Tree Expert, a web-based tool that will help you move from a list of required clocks to a completed clock tree design in minutes. There are two ways to use Clock Tree Expert. You may select the Build Your Own option, or let Clock Tree Expert do the work for you by clicking on the Clock Tree wizard. Enter the clocks for your application in the requirements list. Once you have finished, click the Generate Clock Tree button. In seconds, Clock Tree Expert will create a design that will meet your application's timing requirements while minimizing the BOM count. Click each block to assign part numbers. A parametric search window will appear to help you quickly find the part you need. Once you have picked part numbers for each block, congratulations! You have a completed clock tree design. You may then create a bill of materials list by clicking BOM, complete with links to datasheets, online ordering, and factory customization options. Clock Tree Expert will create a report of your clock requirements, block diagram, and BOM list. When you do not know where to begin your next clock tree design, Clock Tree Expert will get you from clock requirement list to bill of materials list in minutes. Try Clock Tree Expert today.
Pros and cons. The pros are the thanks to its digital demorero architecture provides very high AM separation in the phase noise measurement. And cons, we have AM noise is greatly surprised by the high slew rate of the clock. It typically does not contribute to the overall clock jitter. Applied in Ecuador, the resulting overall system function is applied to the measured phase noise trace Warrington filter before integrating the jitter in the defined jitter integration range. It's a video about digital clock matrix 88 33,404 multi-channel DPL LDCO programmables of 158 jitter time item solution.
My name's Ian Dobson. I'm a system engineer here at IDT, and I'm going to talk to you today about our recently released Clock Matrix family of products. Specifically, I want to talk about how they can be used to address jitter attenuator and clock synthesizer applications. IDT's Clock Matrix family addresses a wide range of applications using 3 subfamilies of pin-compatible parts. I'll be focusing on the 8A3404X products, which are focused specifically on clock synthesis and jitter attenuation use cases, including synchronous Ethernet and optical transport network designs. There's another video available discussing the full Clock Matrix family. Using IDT's Timing Commander software and the 8A34041 device, which is the largest device in the 8A3404X synthesizer jitter attenuator family, we'll see how powerful and flexible a clock matrix solution can be. In this example, there are 8 PLL channels set up with their own individual, independent frequency plans. 4 of the channels support 2 integer output dividers each, and the other 4 support only 1 each, for a total of 12 different frequencies on the 12 differential outputs. Each differential output can be split into 2 LV-CMOS outputs if desired. On the input side, there are 8 differential inputs that can also be split into 16 LV-CMOS inputs. Any of these inputs can be mapped to any or all of the PLL channels. Looking at this, many customers may say, I don't need that many PLL channels in a single part. I may only need 2 or 3 channels. And of course, we have parts for that. However, customers often approach us a little later and say, can I add another channel to this? And then later another and another. And soon they find themselves using the entire part and implementing their whole clock tree in a single part. And last but not least, the Clock Matrix devices will give you performance in the 150 femtosecond range for RMS jitter. This allows a large number of applications to be serviced simultaneously with the desired performance levels. IDT is proud to release the Clock Matrix family of powerful and flexible devices. Please check on IDT.com for more information on these newly released parts, or contact us at clocks@IDT.com.
And finally, we have the conclusion. The RNSVSWP offer the functionality need to test load jitter, close input SSC of mode and LC on mode. It provides very high AM separation in the phase node measurement and excellent phase node sensitive for preset jitter measurements on low jitter, close for modern high-speed digital designs. And well, thanks for your attention and goodbye.